Hi, everybody. Have you ever wondered how Netflix really knows which movies you will enjoy? How banks instantly decide whether to approve you for a loan or not? Or maybe have you seen the e commerce website magically recommend the perfect product just when you need it? Behind the scenes, it's one of the simplest yet most powerful algorithm making these decisions. It's called the decision tree. Today, in this episode, we are going to break down how decision tree really work in a most simplest and fun way possible. Using a lawn mower example, imagine you're a salesperson. You want to sell the lawnmowers to as many people as you really can. Now you notice people with large yard tend to buy the lawnmower more. So you would try to reach out to those people who own the large yard. Similarly, people with higher income, you notice that these are people who buy my lawnmower even more. So you will try to reach out to those people who have higher income. So what's that threshold of higher income? Above 60,000, 55,000, 85,000, 150,000. How do you decide on this? That's where the decision tree really comes in. It helps you decide what are those thresholds, what are those income parameters, what's that lawnmower criteria, lot size criteria, beyond which you want to really target those people. They could be your potential buyers. This algorithm really makes money for you. It tells you whom exactly to reach, whom exactly to reject in the loan process, or which movies to play for that person. How this algorithm really works and how to use it. This is what something we're going to learn in this video. Decision tree can work on both classification and regression dataset. It can even learn the nonlinear relationships in the dataset. It does not require to have much technical knowledge before using it. And the most interesting part of this algorithm that it's a white box algorithm. Unlike the algorithm that ChatGPT uses, which is actually a black box algorithm. Now, what's the difference between white box and black box? White box means you can explain its results. Black box means you cannot explain its results. That's the biggest difference. In a court of law, if somebody asks you, why did you reject this person from his loan application? If you use the decision trees, you can explain because this person fell into the category of people who typically do not tend to return or pay the loan back. That is the reason we have rejected this person. Why did you play this movie? Because this person saw X, Y, and Z movies, that's why we recommended him Z1, Z2, and X2 movies. Why did you target this person as your potential buyer? Because this person fell into the certain category of people in the past, because he had higher income beyond certain threshold, because he had a bigger yard beyond certain threshold, I'm targeting this person. There could be n number of use cases of this algorithm. Point is, it explains the data, it explains the decision making, and you can hold your grounds in the court of law using this algorithm. Unlike ChatGPT, which uses deep learning, you cannot really explain why a certain decision was made, why a certain language was used, why a certain mathematic did not hold true, or why it even held true, because it uses something called weights and biases to make its decisions. And you cannot explain those weights and biases. What it does, what decision tree does for you, create rules. Income high, lot size high, this person is a potential buyer. Income low, lot size very high, this person is a potential buyer. Income very high, lot size very low, this person is a potential buyer. both income low and lot size low, this is not a buyer. That's a very simple example. Imagine when the number of variable really increase. Income, lot size, race, color, ethnicity, locality, and so on and so forth. But just know that using race, ethnicity is not legal to use in these algorithms to make your decision about potential people. Classification task. We're going to look at this example. Income column, lot size column, and there are 24 potential owners and non-owners that we are going to learn this data set from. So the data of 24 people is now plotted here. Lot size on the y-axis, income on the x-axis. How do you learn from this data set? Interestingly, algorithm draws horizontal line mathematically based on the majority rule. Majority of the buyers, that's the fill data points, are on the north side of this horizontal line. So these are owners. And these guys, empty points or empty circles are non-owners. That's based off the majority rule. And if the new data point from the real life comes in and it falls here, it's going to predict this person as non-owner because below this line are non-owners, majority, and above this lines are owners, majority. So what it did is it made a decision. It came out with this threshold based on the majority data points of 19,000 square feet. Above this, it's mostly owners. 9 of them are owners, 3 are non-owners. So what's the accuracy? 9 over 3, sorry, 9 over 9 plus 3, that's 12. That's 75% accuracy. Now let's look at another vertical line that we could draw to separate these two guys out. These are owners, but they still fall below the threshold of the lot size of 19,000 square feet. So this vertical line separates these owners from the non-owners. Now we have two decisions. First, based on the lot size, second, based on the income. So we already looked at this section of the decision tree. Let's look at this section of the decision tree. Beyond 84.75 thousand annual income, typically people are the owners. So unlike before, if the new person from the new data set falls in this category, we would have previously predicted this person as non-owner, but now we would predict this person as owner because we have another vertical line here. So this area now belongs to whom? It belongs to owners. This area belongs to non-owners. But what is this guy who is owner doing in the category of non-owners? This person is called impurity. Are impurities always bad? Answer is no. We want to keep the impurities in the data. If we learn 100% of the data, create horizontal and vertical lines for each data point. For example, each of these guys will have their own areas. Each owner will have its own box. That leads to a problem. The problem it solves it is there are no impurities. But the problem it creates is it overlearned from that data. The overlearning is called overfitting. overfitting the dataset. So we already looked at the majority rule. This diagram shows you that you have overlearned from that data. You drew too many lines, too many horizontal vertical lines, and almost each point, for example, this guy has its own area or own group. So if a new person comes here from the new data set, he will be marked as owner. Potential chances are below this person would still be a non-owner. So what's the solution? You do want to learn from the data, but you don't want to overlearn from the data. Learning everything from the current data set that the new data set would exactly be similar or exactly be the same as the old data set that we learned from, that's not going to happen. You really want to test this algorithm in the real life, in the real world, and data points will not follow exact same pattern, but it will follow the generic pattern that's described by the data. People with higher income and higher lot size would be the owners. This leads to a good amount of accuracy, let's say 70%, 75%, 80%, without learning too much from the data set, you're good. If you're reaching the level of 100% accuracy in the learned data set, there's something not right about the learning that you have done. You have overlearned from that data, and that's something you don't want. So, how does the algorithm really work? It uses variable 1, variable 2, variable 1 in our case was income, variable 2 was lot size, and so on and so forth. And it can use n number of variables to learn from. And it will create different thresholds, different splits, vertical lines, horizontal lines, and it will find the impurities. It will try to reduce the impurities by creating further splits. It will rank the results, select the best results, and repeat this process. And it continues in this loop until it hits something we define in the hyperparameters called the max depth. How deep really you want to go in the tree, or when it finds out that there is no more improvement in reducing the impurities. Scikit-learn, there's a package in Python that uses recursive partitioning or CART, C-A-R-T, CART. CART is greedy algorithm. It keeps moving on and never looks back. What it does, it gets close to the optimal solution, but it does not exactly reach the optimal solution. It gets reasonably close though. The challenge with CART is it's only a binary split or a two-way split, yes or no. But if you want like a three-way split in the CART algorithm, you like yes, maybe, no. This person may be a buyer. This person is not a buyer. This person, yes, is definitely a buyer. If you want like a three-way split in your predictions, you can use ID3 algorithm, which allows you a three-way split. How do we measure the impurities? First way is Gini index, second way is entropy. They both yield same results, if not same but similar. Let's use this example of iris dataset to understand this impurities better. Iris is a flower. It has a certain petal length. It has a width. There are three kinds of iris flowers. One is setosa, virginica, and versicolor. Algorithm makes a decision based on the dataset it's learning from. If it's smaller than 2.45 centimeter for the petal length, it's 100% true that it's going to be a setosa. What if it's false? You got two more decisions to make. Petal width. See the parameter change from length to width. So the petal width, if it's smaller than 1.75 centimeter, it's going to be a versicolor. If it's more than 1.75 centimeter, it's going to be a virginica. Simple enough, right? How do we calculate the impurities? Let's calculate the impurities for this group of flowers. Impurities means in the data set of virginica, you are seeing either setosa or you are seeing versicolor. You don't want these two guys in the set of virginica. And we want this Gini index to be low as possible. So the formula for Gini index is 1 minus 0. 0 belongs to setosa. No zeros or sorry, no setosas are found in the validation data set of virginica, which is pretty good. So this number leads to 0. 1 over 46. 46 is total number of observations in that data set. So 1 plus 45 is 46, and 1 is 1 impurity, which is versicolor. So 1 versicolor was found in the validation data set, and 45 over 46 is pretty small number, which is uh, um, practically close to 1. So the bigger this number or closer this number to 1, the smaller Gini index you're going to get. And that's how the Gini index really works to tell you how much impurities. This is pretty small, 0.0425, and we're going to accept these results. Tree structure. You look at this tree structure, that's how the decision tree algorithm really works. For example, let's look at this data group and try to find out the probability. We also call it accuracy. Setosa probability is 0% in this group. 0 over 54, 49 plus 5 is 54. That's 0% probability of setosa in this group. If the new data point falls in this group, 91% chance is it's going to be a versicolor, and 9% chance is it's going to be like a virginica. So you got 91% accuracy. Always remember the final decision, or the final prediction is made based on the terminal node only of the whole decision tree, not the intermediate nodes. We already talked about overfitting. We don't want the overfitting. We want fewer splits. We want the splits in the data, but not as many that it's learning each data point by itself. How do we avoid overfitting? There are hyperparameters or parameters for regularization. Regularization in simple language means restrictions using hyperparameters. You define the maximum depth, minimum samples in the split. So you want minimum samples in the split. You want, let's say you define it to be 5. So this split is not going to work because you want at least 5 data points in that split. Similarly, minimum sample leaf. So number of sample or number of observations a leaf node must have, you can define that. That will reduce or create some restriction that will reduce the learning and reduce or that will reduce the learning. Minimum weight fraction, minimum leaf nodes, maximum number of features. Let's say you don't want all the columns, you've got hundreds of columns and you want to use only 25 most important columns out of 100. This way you are limiting the learning from the data set. This is the difference between regularization and non-regularization. Let's say you define minimum sample leaf size to be 4. So here is the data that it learned from with no regularization or no restriction. We created these rectangles for each of these data points. Since the minimum sample leaf size is now defined to be 4, this will count as impurity in the larger data set of the yellows. Or yellow in this case may mean buyer versus non-buyer. You don't want these little triangles to create its own group. You want the broader or generic learning pattern, and we will accept the impurities. How to avoid overfitting or overlearning? There is something called training error rate. So as you train it and you compare it with the validation data set is a trial test data set. You keep finding out what's my error percentage. Terminal error rate will continue to reduce as you learn, as you continue to learn, and it might become zero after a certain point because you overlearned. You created the rectangles or triangle lines for each data points. So error goes down to zero. And somebody who is less experienced might think, oh wow, my error went down to zero. But when you really compare it with the validation error, error goes down until certain point, let's say from 1.67 to 1.47, but it really starts climbing up after that point. So you don't want to overlearn from the data that your validation data set is giving you, or you really have overlearned. You are running different models each time and trying to find out the error percentage or error rate. This is your optimal data point, which is you cannot learn beyond this point from this current data set. You can use the decision tree in regression too. By regression, I mean a continuous variable in the target column. For example, right now we looked at yes, no, maybe, just three possibilities in the classification task. Now, if you want to use it for regression, for example, you really want what kind of lawnmower is this person going to buy? Whether he's going to buy like a $2,000 lawnmower, $3,000 lawnmower, $4,000 lawnmower, 5,000, 6,000, based on the previous data set, and you're trying to predict the new person, that task becomes like a regression task. Instead of using impurities as your parameter to judge whether the algorithm performed correctly, now you use mean squared error. Disadvantage is they generate the same value for each observation at the leaf node. So it creates this scatter plot just like what we did before. This is an example of the scikit-learn version, and it creates or gives you the mean square error, MSE, and you want to judge your algorithm by mean square error. It creates an average and takes the error from that average. It's still a decision tree, it's still reliable, and it can explain the predictions it made. What about the non-linear dataset? Yes, it's able to accommodate the non-linear continuous variable and it will create this kind of learning. We have defined the maximum depth to be 2. When you define maximum depth to be 3, it creates better learning. It's following the pattern. You can go on with 4, 5, keep on increasing the, let's say, sample leaf size. So you create a very fantastic learning and you are almost learning exactly what data is telling you. What if you learn with no restrictions? Just learn everything from that data. You learn too much. You just exactly plot the, the current data set practically. When the new data point comes, let's say here, you might think it's a non-buyer and you might think this person is a buyer. But in reality, this is just another, it might just be here. Instead, you thinking it to be a little bit above. Those are the problems that are associated with learning too much versus learning generic pattern. There is something called principal component analysis. You can transform the horizontal, vertical, like step-by-step lines to vertical lines, and it creates the learning easier for the algorithm and algorithm tries to give better results, expected to give better results using this approach. The problem is, since you transform this, the matrix is now transformed, and now you cannot explain these data points. How this transform to this green set. So these are not explainable anymore, which was the biggest advantage of using the decision trees. Feature engineering or feature importance. Feature importance is pretty handy feature of the algorithms typically used in Python. It rates the feature. By feature, what I mean is column 1 is a feature, column 2 is a feature, column 3, and so on. There could be n features in the data set. For example, this is playing a dominant role in predicting the target variable. If this is playing the importance of this would be 1. If this is playing, let's say feature 3 is not at all contributing to the final prediction, its importance is likely going to be 0. Advantage of using the trees. It's pretty easy to use, good and accurate predictions. The biggest advantage in my view, it's a white box algorithm, creates understandable rules that you could explain to your customers. Can it be used for uh, variable reduction as well? Performs variable selection automatically. You don't have to interfere which variable to select, which column to select, which feature to select. And it's not sensitive to outliers. There can be some impurities, and we will accept those impurities. And it can work on non-linear relationships as well. Disadvantage is you can overlearn from this data, and there are no diagonal lines. There are only horizontal or vertical lines that split the data set. Let's look at the example in Python. We're going to learn from the healthcare data set. It contains 10 years of clinical data of 130 US hospitals. Each row represents a single patient. Columns include characteristics of diabetes patients. Prediction is binary, which makes it a classification task. Question is whether the person will be readmitted to the hospital within 30 days of discharge, yes or no. It's going to learn from the data and see if it works on the prediction data set or not. This is an important metric that hospitals typically try to use to minimize the readmissions. So we got the race, gender, age, admission type, discharge, disposition, whether this person was discharged or not, time in hospital, number of lab procedures, all those bunch of hospital related information. Readmitted or not is a binary target variable. We're going to find out whether this person was readmitted or not based on uh, a lot of learning we will do on this data, and we'll test it uh, on the validation data set, which this algorithm is not aware of. These steps like splitting the data, preparing the data, separating the target variable from the data, feature engineering, all these we have covered in my first and second video in the same machine learning series. Identifying the numeric, binary, and categorical columns for the data pipeline. Now we build the data pipeline, transform the data using the fit transformation for trained data set, transform the data without using fit transform for the test data set. We'll do the baseline prediction. Baseline is a very crude way to predict using just the majority rule. Majority of them are owners, majority of them are, in this case, let's say the patients who were readmitted, then it will use the same majority idea or the most frequent idea to predict everybody else. It might be at least 50% times right, or sometimes 40%. See, that's the baseline accuracy we are comparing ourselves with. What we find out, the baseline comes out to be 53% baseline accuracy. So 53% times uh, it's predicting it correctly. So either 53% times we got the people to be readmitted, or 53% times the non-readmitted people, or the non-readmitted patients rather. So now we try to do the real thing. Train the decision tree model using decision tree classifier. Remember, it's a classification task, so I'm using a classification decision tree classifier, not a regression task. So I'm not using a decision tree regression algorithm. I'm importing from scikit-learn, sklearn, and I'm also importing like a package for the accuracy score. So I'm training the data set using tree underscore CLF. Tree underscore CLF is where I saved my decision tree. I limited the maximum depth of the decision tree to be 5. If I don't limit it, my algorithm will learn too much. And now I print the accuracy and I test the accuracy now. So this is meaningless. Why? Because checking the accuracy on the trained data set, that's the data set we learned the data from, is meaningless, but we are actually interested in how it predicts the data set which is new to it, that is the test data set. So I'm predicting the test data set and I get like a 60% accuracy. Note that it's better than the baseline accuracy of 53%. That's how this algorithm of decision tree works. Let's try to see how my tree really looks. Since I limited it to num 5, maximum depth of 5, so I get 1, 2, 3, 4, and 5. And the last node is the terminal node, which is used for the prediction of the test data set. I can make it larger and see how my tree really looks. You see this Gini index we really talked about in the PowerPoint. Here the Gini index of 0.452. All these decisions are made based on the binary yes or no answers. Now, let's try to play with the hyperparameters. So decision tree, we are interested in entropy, and we are going to use the splitter to be best splitter. We don't define what kind of split. That's why we are using the best split. Like it keeps doing the same task multiple times until it comes to the best split. We have still defined the maximum depth, minimum number of samples in the split to be 4, minimum number of samples in the leaf to be 2. And now we try to see if it improved the accuracy or not. Here's the train accuracy. Here we put the train data set again in the prediction. This is meaningless. What we are really interested in, what it did not know before. It came out to be 0.595. It depends on data set to data set, but generally what I'm seeing for my data set, I'm roughly around like a 60% accuracy mark. I just predicted from the test data set. Let me split it randomly and try to take out like a random test rows from the data set. If I try to do this prediction on the random test rows of the data set, I'm observing like 63% accuracy. I can further try to improve the accuracy by using something called grid search. If you do the grid search, what it does is it tries to find out which parameters are contributing more to the final prediction. And using the grid search, it tries to run the accuracy. It's running on the same model on different using different parameters. By that, what I mean is maximum depth ranges from 5 to 20, minimum sample size, sample leaf from 5 to 20. So I'm giving a range, and I'm also trying to compare whether the best or random would yield better results. So I'm comparing four different criteria to do a lot of permutation and combination, like using a random search, and finally seeing if that would improve my accuracy or not. Well, in this case, accuracy did not improve significantly. The train data set, I tried it again on train, which is meaningless, as I mentioned. Test data set is real test of the data set. Accuracy stands at like 59.8%, which is better than the baseline, but not better than not doing the grid search. So what I would do with this number, I'll tell my boss the accuracy generally stands around 60% with this algorithm. Either now I change the algorithm or I live with this results if that suits my purpose. So I believe that's all for today. We learned decision trees, we learned different use cases for the decision trees, and we learned how to model a decision tree classifier using Python language. I wish you good rest of the day and good luck with your future endeavors. And if you have a job that pertains to machine learning, let me know. I would be interested.